I'm Braden Whitaker. I'm electrical engineering. We have Andrew McBrenna, who's also an electrical engineer. We have Joshua Everhart, who's an audio engineer. And we have Zachary Davis, who is our computer engineer. Quick overview of what we're going to be discussing here today. We're going to go over why we made it, the motivation, what went into this product. We're going to talk about what our product does, the features, and also how we did it. And Josh now, go to the problem.
All right, so this is the problem that we were presented with at the beginning of last semester. Since the 1800s, metronomes haven't been updated to support the drummers or whatever other musicians have been using them. They don't provide any live feedback, and currently the only way for a drummer to listen to a metronome on stage is through headphones, which can get in the way, especially if your other band members are off time. So our solution to this problem is to design a dynamic metronome that's capable of determining the beats per minute for the drummer in real time, and it's displayed to them back on our UI. Andrew.
So unfortunately, we don't all have the gift that Josh has with perfect rhythm. Some of us are more like myself, where I really struggle to keep a beat. So that's why I would personally actually buy this product if I was a beginning drummer, because it would help guide me to the correct tempo. The other person who should be purchasing this product is a live performer, because when you're playing on stage, currently you have a metronome in your ear pounding at a specific BPM that you set it to. But say your guitarist is a little too amped up and he starts playing too fast. It is your job as that drummer to go up to his speed and then bring the entire band back to tempo. I personally could not do that without some kind of guidance helping me through that scenario, and that's why I would have to personally purchase this product. So, starting out in prelim, we set requirements for, and our customers set requirements for what he needed this device to do. And very first off, the user must be able to input both the BPM and the upper and lower time signatures. The product must be able to detect simple rhythms, and Josh will later be describing the difference between simple and complex rhythms. We must be able to display that real-time BPM back to the user. It must be cordless with a battery life of at least 4 hours. It can operate while charging, and then it charges via micro USB, which is just standard in the industry, and then it also will display that battery life in a percentage back to the user. And now we're going to show you guys a video demo of what's going on. So what you're going to see in this demo is our drummer is going to start out too low, and he doesn't know that he's drumming too low.
So we begin with setting the BPM and time signature for the song.
But Thunderbuddy is going to
For this case, we've selected a BPM of 150 and 4/4 time. The drummer then begins to play.
Sorry, I'm not a big videographer.
Right now, we are seeing the initial startup delay on the screen.
There is a mild delay at the initial.
As you can tell by the speedometer, the drummer is initially playing slower than 150. He then speeds up, trying to correct, but ends up playing faster than his target, as seen on the speedometer. Again, the drummer starts playing slower to compensate.
What we're seeing now is that Thunderbuddy is helping narrow him in on his target BPM where it needs to be.
And that's why you hear that stutter in his foot, is actually Josh trying to correct what it actually means.
Finally, the drummer begins to play on beat with the help of Thunderbuddy, shown with the needle being near the center of the speedometer.
So I don't know about you guys, but I have a hard time distinguishing when it's off and on. But the testing procedures that I'm about to show you guys shows that he actually was playing slow and he actually was playing fast by our accuracy and precision that I will be showing on the next slide. But first I want to describe to you how the testing environment happened. So we used an electric drum machine in Josh's studio using Ableton to produce that sound. And then we iterated the BPM in decades, so by every 10, all the way from the range of 50 to 250 BPM. We repeated each one of these tests 3 times, and then each individual test was for 30 seconds, or a 30-second time frame. So as you can see on the screen, this is a graph of our percent error. Each one of these blue squares indicate the average of those 3 tests and the percent error for that average. So as you can see, in the lower range, in the 50 BPM range, that is when we were worst or furthest off, and that's because we don't have as many kicks to calculate as accurately. But as we speed up, it becomes more and more accurate, with our sweet spot being anywhere between 120 to 250 something, or sorry, between 120 and 200 BPM. The red line is a linear progression or trend line of our data. I'll now be passing it to Zach to describe how this system works.
So how it works, as you can see from the video, initially the drummer puts in the user input and he starts playing on the drums. And like Andrew described, is the kick drum that we're focusing on. In our device, and we can get into it later, that we actually have a breakout Adafruit I2S communication breakout board that is a microphone for sampling the actual user audio while he's playing. And then these take the audio and put it into .wav file. Now that gets sent to our CPU. Our CPU being a Raspberry Pi 3B+. This was picked so we could get the product working, but Braden will talk later that we can actually reduce this through actually testing and procedures that we don't need something this heavy power for CPU. We don't need as many cores, this much memory. We don't need this much processing, which can reduce your costs. And then finally, after the CPU does all the calculations for both the sampling and then determines the filtering of the audio and what the BPM is, it finally updates the user to this touch screen right here, as we saw in the video, and it shows every time, and it's about 10 seconds or so between each BPM of it. Now we'll talk about a little about the algorithm and the flow. Is first, when the .wav files come from the sampling from the actual microphone itself, we have to filter out all the audio, and that because we have all the other instruments that are playing, we want to focus on the kick drum that focuses on the BPM. And then now we want to throw it through a gate, or other known as a threshold, that basically once we hit a certain threshold for the actual dB, or the loudness level, if you guys aren't familiar with dB, so that we know when the actual kick hit, because we're only focusing on kick. And then finally, we throw it through Josh's simple beat detection algorithm, which will look at patterns, and he'll go in more depth here in a little bit and determine the actual BPM from the upper numeral and the BPM user input. So now I'll let Josh talk a little bit about music theory and how it works.
So as you can see here, we have a picture of a measure indicated with both our upper and lower time signature. On the top, you can tell that the top indicates the number of beats per measure, or bar, depending on your phraseology, and the bottom indicates the value of each beat. For our project specifically, we only needed to worry about the upper time signature since we're dealing with simple rhythms, but if we were to continue this project, we would also need the addition of the lower time signature, which is why we've added it to the UI. So, like we were saying before, there's a difference between simple and complex rhythms. Our definition defines a simple rhythm as each kick hit landing on the beat of a measure. If we were looking at a complex rhythm, we would see these beats land anywhere in the measure but still be on time. That's a little too random for us to take into account right now, and as such, we're just focusing on simple. So to run through our diagram, we start with our filtering. This diagram shows an audio spectrum for an entire drum set. The area in green shows our kick drum, which is exactly what we're trying to look for to determine our rhythm, while the drums in red, the toms, snares, cymbals, and hi-hats, are all extraneous data that we don't want to have to process for our algorithm. To take care of this, we used a moving average low-pass filter with a cutoff frequency of 100 Hertz, which you can see here, which is iterated 4 times to get a very sharp cut. As you can see, the kick drum is still loud, while the other drums are no longer present in the audio file, and now we're able to go through our gate process. I designed this gate based off of an Ableton program that I use, and the two main important things here are the threshold and our return value. So we wanted to set our return to be 0, so it's the same dB as what's coming in. And then our threshold determines what level goes above and what level goes below. So brief run through, we take in all of our audio samples that the drummer plays into the box, and from there we determine the maximum level for that drum kit. After that, we set our threshold to be 6 dB lower than whatever that maximum level is to make sure that it's a dynamic gate that can work in many different scenarios. Whenever the threshold is reached above, and if the previous has been below, we know that we've achieved a kick hit, and we can now finally go into our beat detection. So our beat detection works by running through and taking a certain number of kick drums at a time to determine the BPM happening, and we also determine the time it takes for those kicks to happen, which allows us to return the BPM to the user. This is then returned to the user in the user interface, which I'll now let Andrew go over.
Awesome, thank you, Josh. So this is our user interface. I'm going to start with the speedometer in the center. As you can see, it is currently pointed straight upward. If you look to the top left where you see preset BPM, that is what you saw Josh input at the very beginning before he started playing. And that indicates what our software is going to be comparing against. That is his desired. And then in this bottom box below the speedometer, that is the actual BPM. That's what we have calculated. In this example, our user is straight on target, and that is why the needle is pointed straight upward. In order for the user to reset that BPM, he's going to press the button right here with the small speedometer on it. That will allow him to reset the BPM, and I have an example of that coming up. The same process will be followed for both the upper and the lower time signature. And those are both buttons where you see the 6 and the 8. Directly below that is that play button, the red play button, which will start the detection or the beat detection algorithm. Once the user is done playing, he will press the red stop button, which clearly will stop the beat detection algorithm. Below that is our battery level indicator. This will indicate above 80%, 60%, 40%, 20%, or above 0%. And then finally, when the user is charging while operation, there will be a lightning bolt that appears in the center of that. In the very bottom left, we see our power button, which will allow the user to shut down the device. In the top right, as I mentioned, with resetting the upper and lower time numeral, his set upper and lower time numeral will display there. In this example, we see our user has pressed the push button for BPM reset, which pulls up a number pad, which allows him to put an integer value in there. I will now be passing it off to Zach to describe the specs and features of the product.
So the different features or components that we have involved in this product is obviously this user interface, which is this 5-inch touch screen, which we want to go because it was easy use for the user to just be able to click and then start. It is 800 by 480 resolution. We also meet the requirement that it is battery powered, so this can operate in any environment. We did not make it waterproof, so you have to be careful in outdoor environments in case of rain and such conditions. And we did get our 4-hour requirement for the operation. It's actually 5 hours, which we will also go over later because now we can reduce the cost by a smaller battery. So this was just for prototyping to actually get the product to work. And then we do display the battery life, like Andrew mentioned, in that bottom right-hand corner of the actual screen. We're capable of detecting that we need to do between 50 BPM to 250 BPM, and it works for all time signatures, so that upper and lower numerals, which is 4/4, 4/6, any combinations of the upper and lowers that you can get from music. And if we continue talking about features, this actual enclosure is a 3D CAD modeling CATIA model. It is 3.5 inches high and 3 7 inches wide by 6 1/8 inch long. It was highly restricted due to the screen because the screen is much bigger than most of the rest of the product, and we want to make it aesthetically pleasing. So we kind of had to build the dimensions to that because the Raspberry Pi and the power regulator and the little mic and the battery are all much smaller than that. It does have these ventilation holes on the side here, which we placed into the actual design so that we could allow for breathing for the hardware to cool down so that it wouldn't overheat. And then we also have these 2 access ports for both charging the Thunder Buddy over micro USB and also the power switch to turn it on and off. And then those are the actual CATIA models that we created earlier this semester, with obviously the holes right there being just screw holes that screw the screen right in, and then currently it's just attached with Velcro. So now I'll pass it to Braden, our team lead, and he'll talk about the overall cost of the product.
All right, so our prototyping cost for the product you see right here in front of you, you're looking at about $150. However, we move to mass production. We're hoping to get that done closer to about $100. A couple ways that we can do that is we're looking at implementing a custom PCB. We're looking at using a less powerful processor. As we mentioned, we don't need the Raspberry Pi 3B+, and also a smaller battery. Overall, our team used about $520 to create this product.
Before we move on, I just want to mention the reason that we think that this is still a reasonable price is because there is no other product like this on the market. There's no other real-time beat detection system. As we mentioned in the very beginning, we've been relying on the mechanical metronome since the 1800s. So this is totally, it's introducing itself to a new market.
All right, so moving forward, some features we'd like to see in the next iteration of the product. We would like to have tackled that complex rhythm detection. We would like to use the professional UI developer, make it a more professional looking UI. Obviously, as mentioned, we'd like to reduce that price point, try to get more like $100. We would like to reduce that delay you saw in the startup of the product, and also MIDI integration with DAWs.
Thank you for your time. Are there any questions?
And anything technical, we do have slides for that of how it works.
Danny.
So the video you had demonstrating at the very beginning, it looked like the refresh rate of it was kind of a long time. And if you're playing the drums, you're off beat for that long, and then you see you're on beat, I think that it seems like it's a really long time for trying to get back on beat. So how would you address that, or how do you guys address
So
that?
currently, the actual communication, and if I may,
He's gonna pull it.
Oh, yeah.
Here you go.
So the current communication that is causing that update to the actual, can you go to UDP? This one. So the current actual way that we're communicating between the Python and C++ is through this actual socket, which is wireless communication. And that currently, why there is that late delay I'm sorry, are you talking mostly about the startup or for the?
So like when you're actually playing, it looked like it would jump.
You're talking in between, I apologize, yeah, so that's actually, we won't get into any of that then. That is actually because we are taking currently with the microphone, the I2S Adafruit breakboard is taking a sample at 8 seconds, and that's something we would want to reduce because currently Josh's algorithm, it needs 2 measures to determine, because it's basically looking for the pattern over that 2 measures and determines the pattern for that so that now the hardware knows that pattern and can determine the beats per minute. We want to try to reduce that as well. That is something we did not mention, but it can go down all the way to 1 second. And then I would even like, if I had more time, because currently we're using Adafruit's documentation for that, to create my own I2S communication protocol that would allow to go even less than 1 second, so we could even have a higher refresh rate. But currently, the big thing that's restricting us is that we need those 2 measures for Josh's algorithm to set the BPM.
Thank you for the question.
Bea?
I think Bea.
Well, it's a simple question. Oh,
No,
Go ahead.
please go.
where does the processor's sense of absolute time come from?
That comes actually
It comes based off of Python.
from the operating system.
So the way that we run it is based off of chunk sizes in the audio file. That's how we look at the maximum dB level and also determining if there's a kick happening. So the way that we've determined time is just by adding the number of chunks that have occurred over that time period to detect 8 beats.
Okay, so you're using the real-time clock
Yes, sir.
processor.
Yeah.
So in your video, and you were talking about restrictions, you're saying it can't detect complex beats. So my real question is, with your example, you were doing just a steady kick drum on the first beat of the measure. What made you pick the bass drum as your detection versus like your hi-hat, which was a constant like 1, 2, 3, 4, 5, like 1, 2, 3, 4, 1, 2, 3, 4?
So the main reason I selected this one was based on decay times for the actual sound coming out. The bass drum allowed us to get a much larger time to be able to detect if it's happening. If we're looking at the hi-hats, most of the time you're playing 16th notes or 32nd notes, and it's going to be too quick for our audio file to be able to detect it.
Dr. Berger.
So, speaking of weeks, take me down a little bit into the weeks so I can understand
Okay.
what you're doing to detect. Because as I'm watching what you're presenting, I see information in the time domain, I see information in the frequency domain, and I'm trying to detect some specific signal. Help me, am I doing one, the other, or it looks like something of both?
So, like I said, we start off with the audio filter just to get our kick drum. And then from there, we enter our gate program.
So what is that? Tell me what it is.
Absolutely. So we run through it, essentially, we look at each 8-second file as it comes in, and we split it into 20 millisecond chunk files. From there, we iterate across all of those chunk files for that 8-second sample and determine what the maximum level is for that specific file.
Normalization.
Exactly. So from there, we set our gate threshold at 6 dB lower than the maximum for that specific file. And then we iterate through them again to determine if the current chunk is above our threshold and if the previous chunk was below the threshold. If both of those conditions are met, we know that a kick has taken place. And as such, we're then able to register that and then output it to our beat detection, which then takes in our upper time signature like we stated before. So an example for you, if we're running in 4/4 time, we're going to need 8 kick hits to be able to determine the BPM that our user's playing.
Why do I have to break life into 20 millisecond chunks?
That was the best way that we could get it to work under our circumstances of playing. It was
Because then you're
testing.
doing detections of each chunk relative power level, and so that defines the resolution. And then you look at the next 8-second chunk, and you,
So it's 8 seconds split into 20 millisecond chunks.
I know, but you do it 8 seconds, and then you go another 8 seconds, and
Yes.
But that's the reason why you have that massive latency. If you were to slide that interval, that would allow you to reprocess, if you will, everything but the oldest 20 milliseconds. I'm not convinced that you need to do things that way, breaking it up into time slices. Something like a spectrogram, I think I saw Zach with an interesting picture like that, where I could look at frequency content over time, or continually sliding time. That might be another approach.
We did actually give that an attempt, and we actually ran into an issue with overrun that we were just able to recently solve that last week. And as a result, we were just looking at each 8 seconds individually, but prior to that, we were running on a continuous looking as it goes. But the overrun issue, I don't know if you're able to talk about that a little bit more.
So basically, it was an issue with the actual buffer size, and I don't see Dr. Seward here, because we actually talked about that last semester, of the audio, the sampling information that's coming into the buffer, the actual mic itself, was getting filled too quickly and we were getting overrun. And what that essentially happened was it was causing these giant spikes that were totally random in our actual wave files themselves. So then the beat detection algorithm was getting fooled, thinking that was a hit with the kick drum because it was such a high dB level that it was confused. And so that was fixed later after Josh had already tweaked some of his code. That was later fixed by when we finally determined that it was the buffer size that was causing that, and we were able to increase that.
But with more time, that is something that we could have.
So still, you could address the prior question by being able to slide even with exactly what you have now, and therefore you would dramatically reduce the latency.
Thank you.
Related to that, did you at the beginning of this project estimate the size of the buffer that was going to be required, even if it's a FIFO buffer? How much data are you going to have in memory at one time?
You're saying
Or
specifically
did you just walk into it?
You're saying specifically for the audio buffer itself? That was not estimated at the beginning of the project.
Okay.
Even though Dr. Seward and I did talk about that last semester, it was something that happened to get overlooked and ended up coming back to bite us later in the project.
Cole, did you have a question? You mentioned that you plan to do MIDI integration with DOS. I was wondering if you could explain that to me.
Absolutely. So a lot of drummers are now using electronic elements in their performances. And so we'd like to be able to use this device to be able to send it to their electronic software that they're using to tell that device what the actual BPM is as it changes throughout their performance, so they're not stuck to one time and get off.
So did you make an early on decision that you were just going to use wave recording? And then is that a CAM wave recording program for generating a wave file?
Yeah, that was actually the suggested route to take by Adafruit documentation itself with that I2S means microphone. And so we initially got that to work, and so we started going with that. And like I said, if I were to redo this, I probably would not use, it's a record, which is a Linux function that was added to the module, which I would not use if I had an attempt to do this project again, and I would create my own I2S communication protocol. So
would you consider just doing your own sample and hold and generating a stream of samples?
My own version?
Yeah.
Yeah, correct. I would basically have more control of everything that's going on, because we ran into too many issues with a record itself, and it should have been, I would not do it again.
And you said you fed it through a low pass filter then to do the
You're talking about the dot wave files?
Yeah.
Yes.
Yeah, so we ran a Python library on those files as they came in to be able to just get our kick drum out.
Okay, but again, you just use the library. Do you think you're writing your own filter? Or?
We did, but it would have taken too much time, and with the integration that we had with our wave files already, it made our process for the software integration much more streamlined. That's why we chose to go with Python at the beginning of this project. If we had more time, we would have actually ran it all in C or C++ to make it a lot faster. But to allow for the algorithm to take place in a quick sense, to be able to code it quickly, we ran it in Python.
I believe there was a question about, right?
Yeah, what type of display did you guys use?
You talking about like the language it was written in, or like what?
No,
developer-
the display that you guys have.
We used a 5-inch capacitive touchscreen made by GeekPy, and then the developer was just in Python. It was GUI 0, which is an extension to Kinter.
I showed up late, so I don't know if you covered this earlier, but how do you differentiate between the pitches of different drums? Like, is it placement of the device, like right next to the kick drum, or like say you have a client who plays with a really wide rim floor tom? Like, how would you differentiate between the pitches of the two drums?
So right now we're running a low pass filter on anything past our kick drum frequency. For this project, we were just focusing on the kick drum. If we were to go further, we would really like to expand it to different types of drums and allow the user to be able to set that. But right now, we're just looking at a standard kick drum.
Thank you. Can you fill in a little more of the horizontal axis? I see one data point 10 to the 4 and then not much else.
Absolutely. Yes.
Yeah, so it's a logarithmic.
It's a log
graph.
scale.
It's nice, but fill in some, what are that green section, what range of frequencies am I looking at?
50 to 150 hertz.
You're picking up stuff that's 1 or 2 hertz. You said 60 to 100 and some beats per minute, right? That's the fundamental frequency looking for.
So it's two different frequencies that we're referring to here. This is the actual kick drum frequency, and another frequency that we're looking at is how fast the drum is playing.
So help me again, remind me which ones I'm trying to pull up, because at the end of the day, you're telling me how many beats per minute, right? And that the fundamental signal that establishes that number is something that's the order of 1 to 2 hertz.
So I think you're getting confused between the sound signature from the drum itself is what we're looking at. That occurs between 50 and 150 hertz. That's the physical sound. And then we're then interpreting the BPM, which is how often they're striking that drum.
We go back to the time domain where you show those two things together coexisting. We had a time domain signal where it showed the burst of the 100 and some, and then the repetition of that burst on the time domain
yes.
of the order of 1 to 2 seconds.
Is that what you're looking
No,
for?
you had an actual time domain signal.
We show the kicks.
Oh,
Yes.
excuse me. Thank you. This one.
Yes, that. So what you're describing to me is the frequencies of those individual bursts, and then secondarily BPM is how often those bursts occur, correct?
The green lines versus the frequencies.
It's all the same in the sense that from a mathematical point of view, those are signals that exist, in one case, 1 to 2 hertz, which is the repetition of that, if you will, the individual, and then the higher frequencies, which are signals of those individual bursts. Correct?
I'm not sure that I'm following with you, but I have not taken these classes to back that up.
I guess the mathematical theory behind it is the same. I would agree with that.
It is all occurring in
Yeah.
one
The
time
fundamental
or one
frequencies that you're
frequency.
looking for in the signal are very, very low things. You're seeing the high frequency signals associated
Yes.
with that, which are in the time domain, these
The
diagonal,
downside, yes.
quote unquote. But the fundamental thing you're looking for, those green lines, if you will, those frequencies are 1 to 2 hertz.
Yes.
Agreed?
Yes.
Why did you focus on using air as the medium to measure the beat? The demonstration you just gave shows mechanical contraption driving the kick drum. A position sensor, perhaps on the skins of a snare drum, could produce a much cleaner signal than audio, which has echoes and noise and so on. It occurs to me that mechanical sensors or position sensors would have produced much cleaner signals.
So I have 2 ways to back that up. Our first is we had a requirement that we had to remove and re-remove the device within 20 seconds from the surrounding area.
Okay, click magnetic holder.
That
Next.
magnetic would not hold it for
Alright.
the case of the drummer. The second, we also wanted this to work for electronic drums. That's how we actually tested it, and there's no mechanical enclosure for electronic drums.
Touche.
Yes, ma'am.
In terms of like the user interface, let's say there's a break in the song, or let's say I do a drum solo. It's not going to detect your BPM in that. So does the speedometer just go to 0?
If
that
you
point?
stop hitting your kick, then yes, it will go to 0, but as
Okay.
soon as you reestablish that same kick, your desired preset, say in the case of a solo in the middle of a song, it'll allow you time to just stop using the kick, do your solo, and you can reestablish that same kick.
Well, that just reminds me of a comment on your human interface there. Having the speedometer go to 0 is an indication of there's no synchronization. Doesn't seem to me to be the right thing to do. It's more of a statement than a question.
But we also don't know when.
There ought to be something else, like a change of color or something that just says, don't look at this. It's meaningless right now, whereas when it's sitting over on 0,
It's more than likely the drummer would know that it's meaningless though if he were to stop using his kick.
yeah, but when you have something that's completely out of action, it means, don't look at it. One thing that just says, it's red, therefore don't look at it.
It could be considered, we'll talk it over with our customer. He was actually with us earlier this morning, we were showing everything, so something we can talk with John Markham about, if that's something you'd like to.
I'm going to ask you to speculate a moment. So, given that the average smartphone has a microphone and a processor and a display, what would it take to create sort of a low-cost mass distribution equivalent, and what would be the differences?
So the main reason we didn't choose to go for that option is you're not always going to have a charged phone on tour, and you could get a phone call in the middle of your performance, and that immediately takes out whatever you're trying to use on the phone. Also, there's no good way for your phone to be attached to our drum set, and as such, that was one of our requirements, is we had to be able to attach it or have it close by. The beauty of this box is that you can have it either on a ledge or something. With the phone, there's just too many interactions that we can't take account for and don't want to in the middle of the performance.
Also, I want to point out, during our first testing procedure, he actually received a phone call, and he had a metronome in his ear trying to stay as close, and that way he could vary it as he wanted to, just so for the demonstration of the video. And he got a phone call from Zach. And I asked him, why are you playing slower? Like, what's going on? And he's like, I'm sorry, I couldn't hear my metronome for it, which is proof of concept for why we need Thunder Buddy. And then 2, it's proof that your phone is doing other things, so that you can't keep an account for. Yes, Holly?
So is it just a factor of your refresh rate that on your speedometer it doesn't like continuously swing instead of it just like jumping back and forth?
That is one of the
Is
things
that
that I
what
would
is
like to implement. I am entirely self-taught for Python. So that was a struggle for me during this because I chose Python so that it would integrate better with our beat detection algorithm. In the future, I would use UX, which is a more user-friendly UI developer. And in that, I looked into it, it would be very easy to make a dynamic swing.
Okay.
And that does also come back to also part of it with the refresh that Danny was talking about earlier, that we'd have to have faster sampling instead of that 8-second files per minute.
What's the range on this thing?
Range for
Yeah, like
how
what
close?
if I like tossed it, like not tossed it, but like placed it a far distance away from the drum? How far could
we
it
were able
detect?
to get satisfactory wave files from up to 4 feet away. But at that range, she's gonna have 4 feet away from the kick drum, and at that range, she's gonna have a harder time seeing the screen, and the mic is picking it up. So.
Did you or would you or should you have done research into microphones that are better adapted to receiving a bass signal, like on a kick drum? It seemed to me like you just used the microphone available.
Initially, when we started our designs back in prelim, we had a very low budget that we had to meet, and as such, 3 out of the 4 of us selected the same microphone simply because it was able to take the frequency that we needed and had a low enough cost. And going into this semester, we chose to continue with that microphone as much of our documentation already had that, and then I think Braden had
Another point is that we chose Raspberry Pi. Raspberry Pi does not have any analog channels available to it.
For audio.
For audio. So we had to select the microphone that was putting out digital or involve an ADC in there, and we chose to go first option.
So you're saying we didn't provide enough budget for you?
Yes.
Oh.
My question on that is, why did you decide to stay with the Raspberry Pi instead of going towards a different?
So, Raspberry Pi, at least the version that we picked, this 3B Plus, which is the biggest version they have, we just wanted to simply get the product working, to make sure that it is a viable product, that this could be put into the market. And we were able to determine that we don't necessarily need that big of a Raspberry Pi, we just need something that has 2, and I can actually show, essentially we were able to determine that we only needed 2 processors and only 256 megabytes of memory. So we could downsize the Pi, but the reason why this one was selected was so that we could get it initially working. So we would have plenty of CPU, we would have plenty of memory, so we wouldn't run into any issues along there.
If we went to mass production, I definitely suggest downgrading to a less powerful processor.
Which would help with cost as well.
Any other questions?
So I just understood that right, the microphone you had was a digital microphone.
Yes, it's I2S, which is a digital communication.
Did you observe, so it obviously had A to D inside of it. Did you observe any aliasing between your software sampling and the microphone sampling?
I do not think we encountered that issue.
I'm trying to
We got them off into an endless loop here.
Yeah, sorry, I'm just going back.
He's the most thorough of the group, he's gonna check every avenue for an answer.
If we did experience, our algorithm didn't have a problem taking care of it.
Okay.
Yes, ma'am.
Did you do any testing to see if you guys would pick up any noise from like a bass, bass frequency, like bass guitar?
So that was one issue that we thought we might run into, but it totally depends on how close the actual bass is to our system. If the bass is putting out a dB level relative to Thunder Buddy lower than whatever the kick drum is, it won't activate our gate and it won't affect it.
Okay. And because that is a mechanical sensor, we do get some isolation just by physical proximity.
Could you also create like a shield almost pointed, blocking the signal from like where a bass signal would come from, just to kind of reduce that signal?
It could, but we didn't find a need for it in our testing.
But yes, that would be a viable, if that issue did come up, that would be a viable solution, I believe.
I think, Mr. Kohler, you had.
Yeah, I forgot my question.
Okay.
Was the device tested with a full band to that extent?
It was not tested with a full band, we just didn't have the time to do that full testing. I would like to, but we just didn't have the time to do the testing of that.
And our customer, John Markham, we already told him, and he's already said he's most likely he has the rights to it and stuff. And this idea originally came from a local drummer that he's in a band, and it is hopefully in the next month that if he can get a hold of it, they can test it with the live band.
And he saw our product today, and he's happy with it, and he does plan on pursuing to bring this to market.
I think we had one in the back, and then
Yeah, so what are some ways that you guys could, I don't know, detect complex kick rhythms better? Like, say you have a drummer who's playing quarter note triplets or something like
All
that.
right, so I'm going to start off with saying that this is an unsolved problem that people have been trying to solve for 10 years. I came up with an algorithm for it back in the prelim semester, which I just didn't have the time to bring to fruition. So we might have one that works. It relies on a rolling window, where essentially we just look at each kick that happens and try to place it into a measure in music and see if that actually makes sense.
Okay, yeah.
But again, we just didn't have the time to bring it to fruition.
There's an annual competition by IEEE every year trying to solve detection of complex rhythm in real time.
No one's got me yet.
But if you can, there is money in it.
Okay,
Mr. Comer? No.
Any other questions?
Thank you all for coming.